everyone. Today we will start with the new chapter, nuclear magnetic resonance spectroscopy. Okay. If you try to break down these words, so nuclear, this term it comes from the word nucleus. Okay. Then magnetic, it comes from the word magnetic field. Okay. And resonance, it is associated with frequency of electromagnetic radiations at which there is an increased absorption of the EMR. Okay. So who will be absorbing? The materials will be absorbing. However, here we are talking about that we are talking with or we are interacting with the nucleus. In nucleus, what we have? In nucleus, we have protons and neutrons. Okay, neutrons, they do not have magnetic field. They will not have magnetic field, so they will not be interacting with the magnetic field. So we are left with protons which are positively charged and they have the capability to interact with the magnetic field. Okay, because when we talk about these protons, even within the nucleus, these protons, what they are doing, they are moving, and they are moving just like a top, so which we call precess. Okay, so the protons, they are moving like a top, that means they are precessing, and while they are precessing, they are creating a small magnetic field within itself. Then we have a large magnetic field which we apply externally. Okay, now this external magnetic field B0, it interacts with the magnetic field which are being created by the movement of the protons. Okay, so that interaction, it is being studied over here in nuclear magnetic resonance spectroscopy, and in various chemicals they are having various chemical environment, and due to those variation in the chemical environment, they will be having this difference in the magnetic field also, and due to that change in the magnetic field, what will happen, the interaction of the magnetic field created by the protons of the uh, molecules or the atoms, that interaction will change, and that change in the interaction is being studied in the nuclear magnetic resonance spectroscopy. Okay, so this is the basis of the nuclear magnetic resonance spectroscopy. Okay, so let's move forward. So we have this nuclear magnetic resonance spectroscopy, and in short, it is commonly regarded as nuclear NMR spectroscopy or nuclear magnetic resonance spectroscopy. In some textbooks, you may find it as magnetic resonance spectroscopy or MRS. Okay. Now, as I told you, what does this MRS do? So MRS, it is basically a spectroscopic technique which can help us to observe local magnetic fields around the atomic nuclei. Okay. So in short, what we are doing with NMR spectroscopy, using the NMR spectroscopy, we are trying to understand the variation in the local magnetic fields within a particular molecule or a compound. Okay. Now, when I am talking about this electromagnetic radiations over here, and I am talking about the frequency of this electromagnetic radiation. So, what type of electromagnetic radiation we are basically talking about? In NMR spectroscopy, we are basically interested in RF frequencies or radio frequencies. Okay, so hearing radio frequency waves are used as electro EMR radiations, electromagnetic radiations. Okay, so as we see over here, the sample is placed in a magnetic field. As I told you, there is an external magnetic field having a magnetic field of B0. So the sample is placed in a magnetic field which is basically the B0, and the NMR signal is produced by excitation of the nuclei sample with radio waves. Okay, the NMR signal is produced by excitation of the nuclei samples with radio waves into nuclear magnetic resonance, which is detected by sensitive radio receivers. Okay, the intermolecular magnetic field around an atom in a molecule changes the resonance frequency. The intermolecular magnetic field around an atom in a molecule changes the resonance frequency. How? I will tell you just in a few moments time, and thereby they give us access to the details of the electronic structure of a molecule and its individual functional groups. Okay. Now herein you must understand a fact. Suppose you are having a strong magnet having a magnetic field which is moving upwards from down to up. Additionally, in a nearby place, you are having a tiny magnet. Now this tiny magnet, what it will do? Let us represent this tiny magnet with a green color here. So it will be having a magnetic field. So as you bring this strong field B0 near this B1, say for example B1. So what B0 will do to the B1? When you bring this B0 near to the B1, the B1 should align with the strong magnetic field. Okay. Why it is aligning? This is aligning because this is the low energy state. I hope you have understood. Okay. Now, if you remember when we were kids, what we used to do? Suppose we used to hold a magnet and then we used to bring another magnet when they will be just aligning themselves to each other. Now what we used to do? We used to rotate this magnet in the opposite direction. Okay. Now to keep this second magnet having fields in the opposite directions, what we needed to do? We needed to hold both the magnets together with our hands. That means we are giving some energy. We were giving some energy to the second magnet so that they can stay in the opposite direction or in the high energy state. Okay. As soon as we used to remove this energy, what it would do? It would again flip back to its low energy state. Are you getting my point? We have two systems, system 1 and system 2, say system 0 and system 1. both are magnets, and when we are placing it in the parallel direction, they will automatically regain that position. However, if we want to keep the magnets in such a way such that their uh, poles, they are remaining in the same way. So what we needed to do, we needed to arrange themselves in such a way such that the magnetic direction is in the opposite way. Okay. Now in this case, what is happening? We are supplying some energy. Okay, we are supplying some energy. Okay. Now when we remove this energy, they will again be in the same direction. Okay, so the magnetic vectors, they would be in the same direction. Now what? If you replace this energy with radio frequencies, okay, so what it is doing? You are having, say, this B0 magnet and this B1 magnet, then you are giving some radio frequency to this B1 magnet. So what it will do? It will align, this magnet, it will gain some energy and it will align itself against the B0 field. Okay, and if you give this RF field only momentarily using a pulse or RF pulse signal, so it will just, this B1 magnet, it will just go to the higher energy state, and just after the pulse is removed, it will slowly start coming back to its low energy state. Okay, and how it will be coming to the low energy state? By relieving the, or by releasing the RF pulse or RF signals which it has absorbed. And in this process, we use this, or we record these RF signals to gain information about the tiny magnets. And in this case, the tiny magnets are basically the protons which are available within the nucleus. Okay. So the principle of NMR, it involves three sequential steps. First is alignment, that is the polarization of the magnetic nucleus winds in an applied constant magnetic field B0. So this is what I have told you. When you apply B0, B1, it arranges itself along the direction of the B0, and this is nothing but your polarization. Okay. Then the second step is perturbation of this alignment by the nucleus of the nucleus means by a weak oscillating magnetic field, usually referred to as radio frequency pulse. So what I had told you in the second step, I had told you that we apply a RF pulse so that this B1 magnet, it goes to the high energy state. Right? It has got to the high energy state while you have given the RF pulse, and the next step would be the detection and analysis of the electromagnetic waves which are emitted by the nuclei of the sample as a result of this perturbation. So what you are doing basically, when there is no pulse, then this magnet, it will try to come to the low energy state, and during this low while it comes to the low energy state, it releases the radio frequency signals what it has absorbed while it is going to the high energy state. So these RF signals which are being emitted when this tiny magnets, they are going to the low energy state, it is being recorded and it is being analyzed. Okay. The most common types of NMR, they are basically the proton NMR and C13 NMR spectroscopy. But it is applicable to any kind of sample that contains nuclei possessing spin. Okay. Now coming to the basis of why these nuclei they are acting as the magnets. As you all know, a spinning charge it generates a magnetic field. So this is the curved right hand rule. In the curved right hand rule, what we have, if you have a conductor and the current is coming or going up, then we'll be having a magnetic field which would be generated, and that generation it is uh, in the anti-clockwise manner. So when we talk about these protons moving, so if they are moving in the anti-clockwise way, so we will be having the north pole which will be generated at the top, and south pole it will be generated at the bottom. Okay, so this single proton it will act as a tiny magnet having north pole on the top and south pole on the bottom, and it will be moving in a counter anti-clockwise direction. Okay, the resulting spin magnet it has a magnetic moment m which is proportional to the spin. Okay, in the presence of an external magnetic field B0 which is in the range of 1 to 20 Tesla, there exists two spin states. Okay, two spin states. One is having a plus half and the other is having a minus half energy state. Okay. Now the magnetic moment of the lower energy state, energy plus half state is aligned with the external field, but that of the higher energy minus half spin state is opposed to the external field. Okay. So what it is saying, say we are having a number of protons within our sample that we have seen, and we have applied a magnetic field B0, a strong magnetic field B0, which is having a strength of 1 to 20 Tesla, right? Now, if you look over here, if you consider the first proton, so over here you are having the north pole on the top and south pole at the bottom, and it is spinning in the anti-clockwise manner. So in this way we will be having a plus half spin state which is also called as the alpha state, and it is the low energy state. It may so happen is that it may so happen that there will be some nuclei which will not follow this rule, and this nuclei they are said to have a spin energy state of minus half, or it is also called as beta state. Herein the proton will be moving in the clockwise direction, and accordingly the north pole it will be generated at the bottom and the south pole it will be generated at the top. Okay, now in this case what is happening basically, it is basically some of the protons they are in a high energy state and they are defying the law what we have discussed over here, okay. Now what happens, okay. So as you see, in the presence of an external magnetic field there are two states which are available for a proton to attain to. Okay. Now this is what it happens when your magnetic field is zero. The energy between these two, there will be no gap when their magnetic field is zero. Now, as soon as you are trying to increase the magnetic field, the difference between these two energy states, they are getting wider and wider. Okay, so there will be an energy difference between this plus of and the minus of states. Okay, so the difference in the energy between the two spin states is dependent on the external magnetic field strength. The higher the magnetic field strength you give, the better will be the separation between the two spin states in terms of energy. Okay, the two spin states, the spin quantum number, have the same energy when the external field is zero. That's what I told you a few moments back. But diverge as the field increases. Bx is applied, is the applied magnetic field. I equals to half, and mu is the magnetic momentum of the nucleus in the field. Okay. The energy difference between the two spin states is less than 0.1 calorie per mole, even at 1 to 20 Tesla magnetic field. Okay. The energy difference between the two spin states is less than 0.1 calorie per mole. Now, why this is happening? Why these differences you are getting? Okay, let's move back to this slide. And if you see, I have told that there can be a possibility of two states. The first state, the alpha state, and the second state, the beta state. So ideally you would say that the probability of occurrence of both alpha and beta, they would be same. However, this is not the case. The alpha state is a better, or it is having a higher energy, or the probability of occurrence of the alpha state is higher. Okay, what I am saying, when we are applying a magnetic field, there are transitions where we will be getting alpha and beta states. Okay, energy states. Now alpha is the low energy state and beta is the high energy state. Next, what I am telling the probability of getting alpha state is higher as compared to the beta. Okay, so beta basically they are the rebels, and if you see, the rebels are usually lower in number. Okay, so high energy state system, they lower number of kind of energy states, and due to this mismatch, we are getting these small or the tiny signals. Otherwise, what is happening is that if you see, if the gap is there and these are equidistant from this zero level, and if you subtract the energy, what will happen? This energy should cancel out this energy. Here, this energy would be cancelling out this energy at the same level, say next bx level, right? But that is not the case. We are getting some signal. Now, why this signal is we are getting? This signal we are getting because we are having this alpha state proton on the nucleuses which are higher in number. Say for example, if you are having 10 protons, it may so happen 6 protons are in the alpha state and 4 protons are in the beta state. So this is just an example. So what happens is that when you have thousands of atoms, only 1 or 2 atoms, they will be in excess in the alpha state. Okay, in excess in alpha state, what do you mean? Over here, if you see, in the alpha state there are 2 excess atoms, and these 2 excess atoms, they are giving signals for the NMR spectroscopy. Are you getting my point? Anyone has any doubt? Now coming to some typical what do you call terminologies. The first one is the spin quantum number. The spin quantum number, it is given by I, and I can be half for NMR signal and for NMR signals. Okay. Second is spin, so it can be either plus half or minus half. Okay. Then spin angular momentum S, it is given by h by 2 pi I. So this I would be either, as I told you, plus half or minus half. Then magnetic moment number M, it is given by 2I plus 1. Magnetic moment number, it is M equals to 2I plus 1. Then magnetic momentum mu, it is given by gyromagnetic ratio. What is gyromagnetic ratio? It is the ratio of the magnetic moment of a spinning charged particle to its angular momentum multiplied by spin angular momentum. Okay. Then magnetic energy E is equal to mu multiplied by B0. Okay. Now for E alpha, it will be mu, if you see, mu gamma S. So gamma into h by 2 pi into half multiplied by B0, and E beta, it would be same, gamma multiplied by h 2 pi minus half B0. So this cancels out. We get E alpha equals to gamma h by pi B naught, and E beta equals to minus of gamma h by pi B naught. So what we have, delta E, it would be given by E beta minus E alpha. So E beta is minus gamma h by pi B naught minus gamma h by pi into B naught. So it equals to 2 gamma h by pi minus of 2 gamma h by pi B naught. Okay. So this is what is your delta energy between the two energy states. Okay. Now, as I told you, the nucleus, it will be having protons and the neutrons. When both the protons and the neutrons in the nucleus are even, we have AI equals to 0. So like C12 O8 16. Okay. Then if we have both odd, then we will be having I equals to 1, and the example is C14 7. Okay. And then lastly, one is odd and another is even, that would give rise to I equals to half, 3 by 2, 5 by 2, and so on. However, for NMR spectroscopy, we will only consider the nucleuses which is giving us a I value of half. Okay, and in this case we have a selective number of atoms which follows this condition, or which satisfies this condition, that I would be equals to half, and those are hydrogen atom, C13 carbon atom, F19, and P31. Okay, so these atoms, they are NMR active. atoms. Okay. So you need to keep in mind that when I is equal to half, in the atoms where the I is equal to half, those atoms are only NMR active. The others are not NMR active. Okay. Would be the state when I is equal to 0. So M is equal to 2 multiplied 0 plus 1. So we are having only 0 state. Okay. In case 2, when I is equal to half, so we have M equals to 2. So it would be having minus half and plus half, two spin energy states. Whereas when I is equal to 1, or then we have M equals to 3, then we will be having minus 1, 0 and plus 1 states. So what is M? M is basically the magnetic moment number. So why, what happens because of this? In the case 1, when I is equal to 0, M is equal to 0, we have no spin energy states. In case 2, we have two spin energy states, and both the states are equivalent with opposite signs, and hence finding the what you call over here, the analyzing this by analyzing these two spin states, we will be able to understand the nature of the atoms within the molecules. Whereas in the case 3, when I is equal to 1 and M is equal to 3, there are 3 spin states, plus 1, minus 1, that should have been fine. But in state where there is no spin over there, so 0 spin state is there. So all the states after the excitation, they are not equivalent, and hence over here in the case 3, these atoms, they are not active. Also in the case 1, since we are having only the 0 spin energy state, so the case in the case 1 and the case 3, we will not have the atoms which are falling in the case 1 and the case 3, they will not have, they will not be NMR active, whereas the atoms which falls in the category of case 2, they will be NMR active. Okay. Now here again, if you see the proton spin energy differences, it is the frequency or the energy. Mu is associated with energy, and here we have the applied magnetic field. So as we go on increasing the magnetic field, if you see the energy difference, it increases. Okay. Similarly over here also, if you see, when you are giving a B naught of 2.35 Tesla, we have these components. So C13, it will be giving signal at around 25.2 hertz. Then phosphorus, it should be giving signal at 40.5 hertz. That means at these frequencies, you need to excite these atoms to get the signal. Okay. In F for fluorine, we have to do it at 94 megahertz, and for the hydrogen atom at 100 megahertz. Now this is in short, when there is no field, there will be no spin states. Okay. However, as we go on increasing the external magnetic field, so there will be two states. The lower one will be the alpha state and the higher one will be the beta state. A nucleus with spin at higher energy generates a magnetic field in the opposite direction to the external magnetic field, and in the alpha state, a nucleus with spin at lower energy generates a magnetic field in the direction of the external magnetic field. Okay, the figure relates to spin half nuclei that include the most commonly used NMR nucleus proton, H1, proton NMR, as well as many other nucleus such as C13, N15 and P31.